Probably just in the interest of time, leave enough time at the end here for questions. I'd probably go ahead and get started unless there was anything else sort of high level or programmatic. Nope. All right, cool. So yeah, today is a big day. Thank you everybody who is joining. So we'll be hearing today from Matthew Johnson-Roberson, who I don't know if you've heard the news yet, but is the new director of the Robotics Institute. So there's some pretty big news there, big transitions and lots of cool stuff happening, very high level. So a little bit about Matthew. So he actually did his undergrad here in CS at CMU before heading to Australia to actually work on his PhD. Did a couple, it looks like postdocs, one in Australia, one in KTH in Sweden, before leaving to go to the University of Michigan, where it sounds like he had a illustrious career before coming here. Helped to co-direct the Ford Center for Autonomous Driving, and started, amongst other things, the Drop Lab, and we'll be hearing, I'm sure, about some of the work there in advanced perception to support autonomous vehicles. It looks like both ground vehicles, whole swath. We'll see more about this in the talk, as well as some underwater work and really interesting stuff. And then also Matthew, it seems like very recently has been is the acting CEO of, hold on, don't tell me, of Refraction AI, which is doing last mile delivery for food. And it looks like they're actually in a pilot in Michigan. So all sorts of stuff across the board. I won't steal any more of your thunder, Matthew, but yes, without further ado, Matthew Johnson-Roberson.
Thanks so much, Matt. I really appreciate it. And thanks everybody for coming through. This is going to focus pretty solely on my technical work, but stay tuned. Hopefully, as I kind of get settled in to the role of director, I can come back and do another talk a little bit about directions for the Institute and things that I'm excited about and that hopefully we can get you excited about. But today I'm gonna, let me talk about the title of the talk. So lessons from the field. So I'm gonna talk a lot about sort of what my work and my group's work has been focused on, which is really field robotics. And that sort of grew out of my experiences here. So such a rich sort of history in field robotics here led me to decide that's what I wanted to do with my career. And so I feel really, really honored to have gotten to work with lots of people here and do interesting stuff, and then have the chance to come back and try to give back and help out. So, when I started to think about this talk, one of the things that I like to talk about in terms of motivation is that there's science motivations and perhaps practical motivations. But I think one of the things that got me excited in thinking about any of this was sort of this idea of the future and sort of what robots would mean for that. And sort of capturing that imagination is one of the things that made me want to work on both self-driving cars when I got started here, and then also underwater vehicles. And what that all comes back to is this idea that there's some future out there that is filled with robots doing really interesting and cool stuff, and we're not there yet. And that's why a lot of us want to be here to kind of try to nudge our way to that. So these are some of the platforms in the underwater domain that I've been working with. So these are Ivor 2 vehicles made by Ocean Server that we modified to put stereo camera systems in. And a lot of that work has been dedicated to thinking about underwater archaeology and environment mapping. So this is an underwater archaeology project that I like to use as an example of sort of one of these motivations for the future. This is a city that submerged in an earthquake in the Bronze Age, and that was mapped pretty extensively in 1967. And then we came back with robots to map it, hopefully at higher and better resolution, 40 years later. And really the kind of thrust of my work to date has been really around trying to use field robotic systems in the underwater context to gather lots of information and turn that into 3D models. So this is over 200,000 stereo pairs reconstructed into a big 3D map, but the resolution you get on each sort of pixel of that is quite fine. So you can see individual stones, individual rocks, and this was used to do a full plan of the entire city. And so outlining all the buildings, a number of burial sites, and other things that were sort of integral to understanding from an archaeological perspective what was happening in that city and how people in the Bronze Age lived. So I think that's really cool. That city is in the southern bit of the Peloponnese in southern Greece. And it's still a site you can actually go see now. So there's no sort of controls on it. You can park your RV, as many German tourists did, and scuba dive on it, which is pretty cool. We work with much larger vehicles as well. And so again, all of this is a way of sort of contextualizing what I think is interesting when it comes to thinking about robot perception, the sort of confines and assumptions and challenges of gathering field data from these very expensive, very hard to deploy vehicles has informed sort of a lot of the research that we've pursued. So this is a ROV run by URI, paid for by ONR and others. But for this, we looked a lot at sort of deep water shipwreck. So this is a deep water shipwreck off southern Turkey. Again, same type of SLAM system designed to take stereo images from a downward facing camera and reconstruct them into a large 3D reconstruction with RGB data. So that's the 3D model of it. And then if you get up close and you look at the actual visual texture, you know, we get very fine grained detail. So you can see the markings on the pots. Those are amphoras that used to hold wine or grain, little starfish, et cetera. We've got to do a bunch of diving with the robots, which has been very exciting. And so this is one of the robots deployed on a reef system. And so, you know, thinking about environmental monitoring, pushing them with divers as well. So not just self-propelled robotic systems, but also ones that augment humans. In this particular case, augment marine scientists to gather data about environmental impact and change. So just from a robotic perspective, they have LED flashes, downward facing cameras, GPS when it's at the surface. GPS doesn't work underwater. And the same kind of things on really large vehicles. So this is Woods Hole, Oceanographic Institution Sentry vehicle. And we built some camera systems. We're able to deploy them on those. So these really deep water camera systems that can go to a couple thousand meters. And using that, build these large scale 3D reconstructions of, again, this is bacterial mats off the continental shelf of the western part of the United States, but giving people the ability, primarily scientists and in other cases archaeologists, the ability to understand what they're looking at, right? And so to get a vision of what it would be like to be underwater without the water there and reconstruct sort of these large 3D environments. Some of this work has been done in the context of future space exploration. And so, you know, there's this nice intersections between this and work we've done sponsored by NASA. So this is bacterial mats in the deep ocean. And so those sort of yellow orangey areas are bacterial mats that get formed by these bacteria that are quite interesting, that feed off upwellings that come through the crust of the earth, but incredibly hot and acidic. And so are really interesting when thinking about exobiology of other planets, trying to understand what we can do from a science exploration standpoint here on Earth, using the oceans as a proxy for space exploration. Yeah. So you can see that there's sort of these large scale mounds that get created and we can reconstruct them, not just the RGB information, but also the structure of what we're looking up down there. Now, lots of that is sort of really early work. And so I'm not gonna spend a lot of time telling you about the technical details. If you're interested, there's a bunch of papers that I got to write when I was doing my PhD on how to do SLAM underwater. But what I'm going to focus on is sort of like why that's a jumping off point for sort of where we've moved now, particularly when it comes to thinking about the intersection of machine learning and some of this data. So to kind of complement this or understand why I would have these sort of very divergent interests in both cars and in underwater, you know, this same vision of the future, this idea that, you know, we would be playing dominoes in our cars at some point in the future, I think really motivated, you know, a lot of people to get into self-driving cars and to really pursue that, right? And I always like to kind of put this in historical context, right? That, you know, we've been building these systems as a field since really the 50s and 60s. So this is one of the first self-driving car projects This was done by RCA in the sort of 1960s, where they installed infrastructure into the roads. There were metal cables, and they used those to modulate the steering of vehicles to get them to drive around on a track. And the reason I like to put this in historical context is, as we keep hearing more and more in sort of the hype cycle about how close we are, I think it's always really important to remember how many projects have come before. And so I was lucky enough to be able to work on some in the early 2000s here, but there's this rich history of vehicles, both here at CMU and elsewhere, that talk about sort of where we want to go when it comes to self-driving cars. And, if you think about things like the NavLab vehicles or even the kind of, vehicles that win the Grand Challenge, what they were capable of doing at the time with the kind of number of sensors they had, ability of sensing, I think is quite impressive. And I think one of the things I like to kind of contextualize here is like, while we have advanced quite a bit, the level of performance is sort of moving that technology, particularly some of the stuff that was done for highway driving in the kind of 90s, into commercial products, but not necessarily, we haven't necessarily gotten to some new stage where everything is solved. So still a lot of open problems, a lot of challenges. I would argue a lot of research questions to be answered, despite the fact that there's a massive industry looking at this. So still work to be done at universities, in my opinion. I was lucky enough to be able to work with vehicles that were being made by Ford. So they produced sort of almost production level vehicles for us to then take out and do self-driving car work on. So one of the natural questions is sort of, why is this a hard problem, particularly for self-driving or for underwater, but let's look at self-driving, and I like to go back to, why are you not getting in a robotaxi to go home today? And I think that really comes back in some ways to these challenges around, levels of safety and what's required to roll a product like this out. So what this is a graph of the fatalities per 100 million vehicle miles traveled. And on the x-axis is sort of the years and the kind of sum of those fatalities in that year. So this goes back all the way to the 1920s. And one of the interesting things, if you overlay sort of the introduction of safety technologies, you see a couple of interesting things. Stuff like traffic lights help people not die, which is great. Perhaps not counterintuitive, but still a good thing to know. Modern speed limits, seat belts, airbags, ABS, electronic stability control, et cetera. Now, one of the important things to note here is that this keeps going down, and where you end up is actually a fairly low number of fatalities. So for between 1 and 2, depending on whose statistics you look at. But that's over 100 million vehicle miles. And why I think that's an important number to keep in mind is that is more than you will drive in your lifetime, and probably you and everyone in your family and maybe everyone if you sum it all up. Which points out a thing that I think is perhaps missed oftentimes when we talk about self-driving cars, but it is that humans, despite the fact that there are many fatalities from driving that are, horrific and in many ways unnecessary, we are pretty good at driving as a species. And so one of the challenges is we would need to get to a point where we had less fatalities than 1 per 100 million vehicle miles. And while many people claim to talk about having this or approaching having this, one of the biggest challenges I would argue is how would you show that, right? And so what does it take to demonstrate that you actually are safer? Is it you drive 100 million miles and no one dies? If that's it, right, certainly the full sort of level 4 self-driving vehicles out there have not gotten to that point, right? They haven't driven 100 million vehicle miles yet. So the question is, how do we know if they were safer? But I think more importantly, from a statistical standpoint, is like, what level of confidence would you need to infer that you were driving more safely than that? Is it to drive 1 billion miles? Is it to drive 10 billion miles? Is it to drive 100 billion miles? And if so, then the question becomes, how would you go about testing in that way? And I think those raise these really interesting questions, both from a just practical standpoint, but then also from an ethical or functional safety standpoint. How would you ever design tests to get to that point? So that's why I think this is still a really interesting problem. That's why I think you're not getting a robotaxi to go home, and that's why I think there's still work to be done on this at universities. Okay, so talking a lot about the problem, but how is this relevant to learning? Well, let's talk about deep learning, because that's what everybody everywhere is doing now. That's the new cool kid on the block for the last, let's say, 7 years. So this is not going to be a talk on specifically how deep learning works, but let's just talk about some of the applications. One of the most common applications is you give a network an image and it tells you this bounding box contains a bird, this bounding box contains a frog, person, chair, dog. Really for the self-driving car context, person, car, helmet, motorcycle, etc. Right? You have some training data: cars, buses, trucks, motorcycles. You have a deep neural net. You run that through on your training data. You minimize some loss function, and then you do inference with novel images, and you get out a label truck. Great. Everybody that's taken the intro deep learning class or not been under a rock for the last 10 years knows what's going on with that. Okay, and then obviously things have gotten more advanced. We think about pixel level labels, all of these things. Now, why I kind of think of this as a whole class of problems is that, much of that is driven by these large static data sets that are labeled images. So think of ImageNet or Kitty or any of the other sort of data sets that have come after. But I would argue there's a real disconnect between that and what we do in robotics, which is really think about field robots. So here's some robots that I've been lucky enough to work on the underwater side, or self-driving cars. But there is this disconnect, right? Those are systems that are embodied, that are moving around, that are taking data continuously in streams, and are not the same as static image data sets. Now, let me not undersell how impactful static image data sets have been on the field and on making things work better. But in many ways, we've sort of kind of in robotics, I think in some ways come at this problem from this default perspective that was given to us by the fact that a lot of the drivers of this were these other problems that computer vision had classically, right? So it's, I want to know what's in this image, tell me what's in this image. And that is an incredibly hard problem. And I don't want to undersell the fact that we've advanced incredibly on that, but that's a problem that Facebook cares about, or Amazon cares about, or static image sets and selling you stuff. And then, in robotics, we've been lucky enough to realize, like, okay, that's actually useful for us as well. But I think the paradigm of approaching it from the static image perspective has been one of the things that has sort of shoehorned us. And you see people moving away from now, but it's taken some time. Okay. So I would argue that just labeling lots of images is perhaps not the future for robotics, simply because it is expensive, both in human labor and in real costs these days. And so it has sort of become a thing that is done by people with more money than universities in really large scale. And so there's this, it begs the question, what impact can we have here? And so one of the things, or a few of the things that my group is trying to think about in this aspect is thinking about self-supervision and unsupervised learning, particularly from a robotic context, thinking about the introduction of physics and the known physics of certain medium to do things, and then simulation as another escape from this labeling problem. So, now a paper that I guess is almost 4.5 years old, something like that, was thinking about this problem. Can simulation give us good enough training data to do things in a driving context? So quite a while ago now, but my group spent a bunch of time, which I would not recommend anyone do again, hacking into Grand Theft Auto and using that as an engine to generate simulated images for driving classification. One of the things I'd like to highlight is that sort of the advances in sort of graphics engines and video games, and that as a medium has really pushed the photorealism of these. And one of the nice things about simulation, right, is that you can vary things like lighting conditions and all of those things very, very easily. And so you can begin to address some of these challenges of domain shift and, will it work in daylight or in overcast or in whatever, using simulation engines. And so we took lots of data by running the simulator, in this case, the game forward, freezing the game simulator engine, and then varying the lighting conditions and lots of the other properties to gather data to label. Because this was not a thing that we built from the ground up and we hacked into, it ended up being this nightmarish process of trying to reverse engineer how the game worked to pull out the labels. So that's why I think this was not a thing I would recommend anyone do again, but really as an existence proof to show that these engines really were capable of training things more accurately, or as accurately as perhaps human labeled data. Here are some examples, right? Those are all cars. They're very hard to see, which is good because it means that the network has to get good at learning how to recognize things that are heavily obscured by rain and lighting and all the kind of things that make this problem hard. What we then did is we trained exclusively on simulated data using no real data for pre-training or for fine-tuning, and then compared that to what you could do with human labeled data. Now, one of the key things here is we were trying to capture the domain shift problem. So we would train on one data set and then test on another. As anybody that works on small data sets can tell you, you can get really, really good at overfitting in one data set. And so it's very difficult to do better than that. But what we were comparing here is sort of the trends that happen as you look at simulated data over increasing numbers. And so this is the Kitty data set being tested on. And so this is a simulation data set of 10,000, 50,000, 200,000, and 500,000 images, which would have been far too expensive for us to actually label by hand if we had tried to go out and do it ourselves. And you can see there's this increase in performance. So this is easy, moderate, and hard, which are all key definitions of cars. So, how occluded a car is, how far away it is. And then these are accuracy. So, north of 70% on easy, north of 55% on moderate, and a little north of 40% on hard. Here's some more tabular results. Great. So I think that's one mechanism right now. So there's been a lot of work on simulation subsequent to this. And so I think this field is still developing. One of the challenges I'll point out, or one of the things that I think we've sort of run up against, is there does seem to be some asymptote to the performance you can get on these things. And this really comes down to this domain shift problem between the simulated data and the real data, which many people are working on. But ultimately, I still remain unconvinced that anyone has produced a solution to that problem that really addresses it. So I think that's still a really open and interesting area of research for all those out there looking at it. Sort of another project in this sort of same vein is thinking about simulation, but from a different aspect, thinking about a physics-based simulation, having to do much more with visibility and the sort of nature of perception sensors, and less to do with the actual visual qualities of the images. So this is one of my former graduate students who's since graduated, Yuan, and he's driving his car in Michigan, and you'll see as he approaches a intersection to pull out, he creeps out a little bit and looks left, looks right, and then continues to pull out. And so that's obviously a very natural human behavior. And we thought, is there a way of both capturing why he is doing that? So why does he need to creep out, look left and right? Obviously it's for visibility, but is there a way of capturing that functionally or formulaically? And then secondly, is there a way of expressing how easy or hard that geometry that he was attempting to pull out of is? And so this resulted in a paper a little over a year and a half ago, where he was thinking about how do I assess risk using visibility, and then how do I produce behaviors from a controller standpoint that increase safety or increase visibility before I make a maneuver. Right. So this idea about risk assessment is, what are the potential risks? What can I not see? Where are the cars that I can't see at the moment? And then from a motion planning perspective, what steering and throttle commands do I want to execute to make a maneuver while still minimizing risk or taking that risk into account. So what you'll see here is blue is the ego vehicle. So that's us, that's the self-driving car. Red are other vehicles in the environment. Green is the observable polygon. This is based on a pretty simple model of a 360 LiDAR, like a Velodyne, that's looking around, but that is obviously occluded by buildings, other cars, etc. The gray is the sort of non-transparent regions. Those are places I cannot see. So green is where I can see, and yellow is goal. So that's why I would like to take this left-hand turn at this sort of four-way intersection. Okay. So you'll see, video plays. You'll see the blue car trying to make this turn to get to the yellow star. And what you see there and the red dots are all of the potential locations of other vehicles that I cannot see at the moment, right? And why those exist, right, is that I know where I can see with my vehicle currently. And I also have a sense of the road layout, right? So using a prior map, I know that, this lane has cars that should go 30, 35 miles an hour in this direction, this other lane, et cetera. And so you can make certain assumptions that, cars are not going to exceed the speed limit by this much, and that, X, Y, and Z. And those assumptions aren't really critical. Those are assumptions you state. And then, if something goes way outside those assumptions, you may have an accident, but at the very least, it's not your fault, right? So sort of impossible to drive if you don't make certain assumptions that like cars are not going to exceed the speed limit by, 5X and drive the wrong way down the street. Certainly when they do, you would need to react to it. So this is not a system designed to address that problem. But from a planning perspective, I don't think that is necessarily where you need to spend your time, at least not where the critical problems are for self-driving. So there's a bunch of people that have thought about provably safe systems and planning with forward reachability. But to do this, what we essentially did is we wanted to look at the forward reachability of the current vehicle and where it could end up, right? So we know the system dynamics of that vehicle very well, right? We can model that with whatever level of fidelity we're interested in. And we can define this forward reachable set as every location that vehicle could end up in over some time window, right? And so that means using different steering commands, different throttle commands, where could I go? And looking at that, we can produce a polygon that expresses that in that 2D space we were just talking about. And we can use that as a way of describing, what is going to happen in the near future. We can do that not just for our car, but for other cars, right? So we have other cars that aren't us, but we can define forward reachability for them. Where can they end up? And then we can use all of these things, right, to determine for areas that we cannot see, where could there be a car and where could it end up in the next couple seconds, right? And so when we think about that, right, we have our car, right? We have its forward reachable set. We have the red car, its forward reachable set. We can see in this scenario, right, there's no intersection between those two, which means that we're not going to run into that other car. And so this is a safe maneuver if we were to continue to go straight through this intersection. But what if there's another car in that area that we can't see, right? That is a place where we could have a collision. And so what this allows us to do is to calculate that risk, to quantify it, and then to use that to make planning decisions. So we can slow down because we know we can't see if there's a car over there. And as we creep up to this intersection, our visibility to that lane gets better, and at which point we can decide we actually want to go. And so the things that we do as humans can be kind of naturally embedded into such a system by just using the fact of the geometry, the forward reachability, using the dynamics of the vehicle, and some sensor model that expresses where we can and can't see. Okay, so there could be cars coming from the other direction, in the other lane, and obviously we can see everything in the environment that's covered in green because that's where our laser can see currently. And so one of the interesting things here is if you look at different road configurations, you can have various different measures of safety. So some configurations, depending on where buildings are, depending on where the roads intersect and what angles, right, are much easier for you to know that you're not going to get hit from the left or the right. And this should really kind of register with you intuitively, right? This is how we as human drivers move through the world. There are some times when you come to an intersection and you know this is very dangerous, you need to slow down and you need to look. So why I kind of consider this simulation is we can look at an existing map. So this uses OpenStreetMap data, and we looked at all of Ann Arbor, which is where this work was done, and we were able to calculate the risk of collision of intersections throughout that entire city without having to run a car over any of it, right? Just using the road geometry, the building geometry, 3D models of where everything was, you can produce this assessment of risk and certainly relative risk between them. Why would this be useful? Well, from a global planning perspective, I'm an AV, there are certain intersections that are very, very difficult for me to go through because the visibility is quite poor. Secondly, you can run the simulation by moving your sensors around and say, well, if I had a LiDAR that was in this position as opposed to this position, or could see an additional 10 meters or additional 20 meters, this is how it would change the safety profile of the routes I run through a city. And so we think at a macro level, this is a way that you can begin to quantify and understand how safe your vehicle is going to be, but more importantly, to plan routes that minimize risk for that vehicle or for that sensor configuration and speed profile through the city. Okay, so kind of staying on this same idea of physics, we can think about underwater image physics as another means of kind of getting away from having to hand label lots of data. So this is work done by two former graduate students of mine, Catherine Skinner, who's now a professor at Michigan, and Ji Lee, who's now a research scientist at TRI. Very quick overview of how physics work for imaging underwater. The red thing is a camera, the blue thing is a light. The rest of that thing is an underwater vehicle. The light, can be LEDs or whatever, doesn't really matter. It shines out to illuminate things, typically because when we're operating deep, there is no other light. and it attenuates with sort of this exponential function that's dependent on certain properties of the water. But we can measure those, or you can know what they are in some cases, and you can certainly model them. It hits something on the seafloor, it bounces back, it reflects depending on the incident angle of the light to it and the amount of energy. It attenuates on the way back, right? So it's, the attenuation is photons getting absorbed by particulates in the water. So that happens on the way there and on the way back. It then hits the dome, right? In which case there's a medium that transition between the water, glass to keep the water out of the camera, and then air in the dome, and then the camera's lens. So we know those sort of refractions at each of those locations. We know about lensing effects and other things that can happen on the surface of that glass. And then finally, the camera response function. So that's how you convert from the photons to a 0 to 255 digital response. Great. So we know all those things. What can we do with those? Well, these students thought about using generative adversarial networks as a mechanism to color correct images from the underwater context to make them appear as if they were taken in. So why use this as sort of an example of using physics to get away from this labeling problem is we don't have labeled underwater data, which is like, this is the image as it appears in air, and this is the image that appears underwater. You can do it for tanks, but you really cannot do it in the field, right? So it's a huge problem for the field. You can't drain the ocean and get an image as if the water was not there. So what this requires is us to use a proxy for that, which is we have images and depth maps in the air that are very easy to get. So this was taken with a Kinect camera. So I have some images of computer monitors, a depth map, and I can get that with a Kinect by just waving it around. You can't get that underwater. So now I have some ground truth image depth map RGB pairs. What we want to do is use that data, run it through what we're calling WaterGAN, produce rendered images that are using these underwater imaging effects that we know exist. I just talked about the physics of that. Use those physics to render a version of that as if it were underwater. And then using that rendered version as if it were underwater, compare that with real images I'm taking in real time underwater and try to train the discriminator part of this network to distinguish whether they're real or fake. So what's going to happen here is you're going to get a GAN that gets really good at producing fake underwater images, and then also a discriminator that gets really good at telling the difference between fake underwater images and real ones. We actually throw the discriminator away in the end, but that allows us to train without having any actual labeled data. So really quick lesson on GANs, right? My generator network takes some inputs, can be random data, whatever, create some fake data. I have a discriminator network that says real or fake with real data as the input. And then I train those in an alternating fashion. So I get better at making fake data. I get better at telling the difference between real data. Great. How do we generate this data or this fake data in the underwater context? Well, we use the physics we know that I just told you about a couple slides ago. So we take this generator, a depth map, and an RGB image from air, right? And we apply the attenuation that would come from depth, right? Because we have ground truth depth, we know what attenuation would be applied, right? We then produce an RGB image that is attenuated in the fashion it would be if it were taken underwater. We then have some camera models, right? That think about the other camera lensing effects, the sensor response function, all of those things. And then we end up with a synthetic underwater image. And then we use the discriminator on that to tell the difference between that and a real underwater image that we were just given, right? Now, the real underwater image, right, does not have a depth map associated with it. It doesn't have any labels associated with it, right? But we can use this iterative process to get better at making underwater images from air images that look like the underwater images I'm taking right now. And why we think this ends up working pretty well in practice is that you're using the physics to constrain this. So all you're learning are the parameters of these things, the attenuation coefficients, the pattern of the sensor response function, the vignetting, all of those kind of things, but not letting this thing create any image it wants, only letting it learn the parameters for this. Well, so for time, I'll kind of skip over the form of these, but attenuation has the same exponential form that you would imagine. Backscattering has a convolutional form that we won't have time to go into, but if you're interested, have a look at the paper. And so in the end, we use those things in sort of series to produce this synthetic underwater image. And then using that, right, we can then have a second network that does color restoration, that takes that and then attempts to restore it to the original state. And the reason we can do this, right, is we have those in-air images that we know the ground truth RGB image from. And so we now have training examples to go from the underwater parameters back to in-air parameters. And so just using that in-air data, we can train this thing to then invert the underwater images that we have now in real time to get back to in-air images, again, without any labels for the underwater images. Yes. So we did some experiments with this, both in the field, but then also in the lab to kind of convince ourselves this was working. We did some testing in pure water with ground truths and color boards. And the end result is that you get these fairly color consistent results. So this is real underwater imagery over on the left. You can see it's very green. And then the restored underwater imagery over there on the right. And you can measure on the color boards how well you're doing and all these things. If you're interested, have a look at the paper, but long story short, you can do quite well doing this. And so you end up with closer residuals to the original results. There's a bunch of other ways that people propose doing this that meet with varying results. And yeah, great. Okay. A key part of this that sort of perhaps maybe unintuitive when you first look at it is you're actually able to produce a depth estimation using these networks, right? An intermediate step here is you need to actively estimate the depth from the underwater imagery. And unlike kind of in-air monocular depth estimation problems, there actually is a fair bit of signal in this, right? Because things that are further away are going to be darker. And so not only do you have sort of all of the other cues you would use in monocular depth estimation problem, but you have this attenuation, these attenuation effects that add quite a bit when it comes to thinking about restoring that. That led us to think about doing this with stereo as well. We do a lot of work with stereo underwater. So, can we do the same thing with stereo imagery using the fact that we have a left and a right image, and we know that we can warp between them, and we should be able to get some sense of self-consistency through that. So we end up with a set of geometric constraints that use warping from the left image to the right image, just as you would in air. But then we also have a set of physics-based models that allow us to think about this problem when it comes to reconstruction. So this is what we call underwater StereoNet. This basically produces a disparity map, but it uses left images and right images. It warps between them. It passes them through a color correction model, very similar to what we were talking about before, that uses the physics of underwater image formation, with the result of trying to produce a self-consistent, self-supervised training process that only requires stereo imagery and no hand labels. So if you run this, one of the end results you get out is the ability to reconstruct from stereo in-air images as if they were taken in air, and 3D models from underwater stereo data. So this is the core reef survey we did at the Mellon Institute of Ocean Science. We used a blue ROV platform and a ground truth rock. And then you can see the raw images on the left, the depth map that's estimated from stereo in the center, and then the color correction on the right. And again, what you're looking for here is both the consistency of color, right? So you want things that are further away and closer to appear similar, but then also obviously you want to reconstruct a depth map that is as accurate as possible. Okay. Because we had some ground truth on this, we compare it to, correlation-based stereo methods. As would be expected, deep learning methods do better, but you can do better than sort of off-the-shelf deep learning methods that don't take into account the color correction. And then finally, the color correction, because we have the color boards, we can look and get closer to the mean color of the final result of the color as if it were taken in air. Okay. On that same vein, in thinking about sort of these localization problems that are faced underwater, there's no GPS. You want to globally localize your vehicle. This is work by Tianyi Zhang, who's a current PhD student here at CMU. He just transferred. So if you run into him, go say hi. He's really interested in thinking about doing this same kind of idea, how do we get away from having to hand label lots of data to solve some problem that uses machine learning? He's interested in learning these cross-scale visual representations for real-time localization of underwater vehicles using just a camera. And so a classic problem in sort of AUVs is that you fly around underwater, you don't have any GPS, so you want to globally localize yourself, but you know something about the environment you're in. So traditionally, that usually is bathymetry, so how the relief of the underwater environment looks, and you can localize a vehicle back to that using an altimeter that tells you how far away the bottom is, right? So you can compare those measurements and understand where you are. In that same vein, right, you know, we have lots of remote sensing data for terrestrial problems like satellite imagery. And in that same way, if you're flying a low altitude UAV, you can then, you know, map yourself back into that satellite data. So we want to try to do that same thing, but in the underwater context with imagery, where we have a low flying AUV and some sense of that data, of the visual data that we're looking for down there. So you think about this terrestrially, a typical problem is I have a query image, for, let's say from street view, and I want to find a match to that in, let's say, some remote sensing data. And so I have GPS locations for the street view data, and I have obviously geo-reference global imagery data. So the problem that we have is a little different and in some ways much, much harder. We have typically a ship that's driving on the surface that's taking imagery at really broad scale of the bottom using acoustic sensors. And then we have a AUV that is flying really, really close to the bottom, taking image data with cameras. And we'd like to figure out some mapping between these, right? And so what we want to do is figure out some way of using these visual observations, whether that be from a large-scale reconstruction or whatever, to produce a belief map of where we think we are in the environment. Okay. So the way that this works is that we have these map patches, right, that are some location of an observation from a much larger map. And from that, we want to produce a function that takes us to a belief map. And using that belief map compares the map information and the observation we just took from our cameras. And so we set this up as a contrastive loss problem where you are comparing between observations you're getting from low flying altitude and observations you have from the map. And so we're jointly training a map encoder. So that's pixel to pixel, and an image encoder that takes whole images and tries to tell us where they are or how they're represented into some feature vector. So for data generation, you know, we wanted to get away from having to label. So we take this large map information that we have. So from for this data set, we have data from Scott Reef, which is in Australia. We have a 100 meter by 100 meter area, and we have a 2D reconstruction at 500 meters per pixel, 500 pixels per meter scale. We take the pixel locations from that, we can sample images from that, and then use that in our contrastive loss training process to produce from pixel coordinates, global coordinates in this global observation map. So to then perform inference, we use a Dirichlet distribution. And what we do is we say, okay, we're going to model the distribution of observing the representation of the embedding of Y, which is the feature vector we have right here, in the belief map Z at location U and V. And so what this lets us do is say, okay, well, how likely is it this observation that we're taking right now came from this part of the map or this part of the map or this part of the map? And then using that, we can create probabilities that we can then pass off to another localization system. In this case, we use a particle filter, but you can use whatever you want. Okay, so we're driving our AUV around our map, and what we're trying to do is get estimates of how likely it is we're in this location. And then using a particle filter on the trajectory of where we believe the vehicle to be, we can refine what we think are hypothesis trajectories through that space. And we can compare that obviously with the ground truth real trajectory, which is in red. That work's still ongoing. He's just getting it out into publication. So if you're interested, please check in with him. But the ultimate goal there is going to be to put together a visual localization system that allows us to localize the vehicle using map data and just one monocular camera. In that sort of same vein, in thinking about underwater manipulation, this is a student that recently graduated, Gideon from Michigan, and he's really interested in this problem. So lots of people in robotics are, I'm sure, familiar with manipulation. And so obviously we have that same problem underwater. Ours is easier in some ways and harder in others, right? So we have the added advantage of being able to put things on our things that we want to manipulate, like that kind of very easy to grasp cylinder. but we have all the kind of perception problems that exist underwater. And so this is a push core sampling. The ROV wants to stick that push core into the sediment there and get a sample, which we're then going to take back up to the surface and analyze for chemical other properties. Gideon is really interested in trying to automate this, and it's a sort of really challenging problem because, you know, some of the sort of manipulation work is not that hard, but the perception problem underwater becomes really, really difficult. So one of the biggest problems we have is figuring out how can we see where the manipulator is and how can we see enough of the workspace to be able to grab what we're interested in. So he got really interested in thinking about fisheye cameras that are mounted on the arm or back on the ROV, and trying to do 6 degree of freedom pose estimation in the fisheye cameras using these omnidirectional images. So if you're unfamiliar, right, that's a fisheye image down there. We put some fiducials on the things we want to manipulate to get ground truth, but they're not used in the actual process of doing the manipulation. You can take that large field of view and you can project it onto a sphere, then you can try to produce perspective images from it, or you can sort of operate it on it directly. So we chose the latter. So he's trying to operate directly on these fisheye images and address the issues of large distortions within that, right? And so these large distortions, right, lead to ambiguities in the apparent orientation depending on where you are with respect to the center of projection of that camera. And so that's obviously the thing you need to compensate for, because if you want to manipulate these things, you need to figure out, you know, exactly where you should be and where you want to go. Okay. So there's a lot of different ways that have been proposed: cube mapping, adapting samples to a sphere, representing it as a graph, spectral analysis. And so what he ended up doing was producing a framework to take region of interest-based networks for pose estimation and have them work directly on fisheye images, and then produce a underwater fisheye pose estimation data set in kind of a natural environment to be able to test and train this. So what he wants to do is use this spherical mapping to take these images and eliminate the distortion, right, by mapping them back onto the sphere, and then being able to inversely map them onto the sphere so that you have something differentiable that you can pass through your network training process. So those are just the equations that govern how these things map onto a sphere, and then how they map back from a sphere into projected space. And what he wants to do is figure out if there is a tangent plane that he can project onto from this part of the sphere, and using that tangent plane, then perform the identification and pose estimation in that tangent plane, and then pass that all the way back through those transforms to get it in relative coordinates to the body frame and the manipulator's frame. Okay, so why this is challenging is if I have this spherical image, right, I have the fisheye's optical axis and the fisheye's viewpoint, and I'm interested in the position of the thing I want to grab, right? So that's the rotation and the X, Y, and Z location of the T handle in that spherical image. So this virtual optical axis is created from a virtual image, and the apparent viewpoint that appears if I project from the spherical image back to this virtual image, and that virtual optical axis then tells me something about the location of the T handle in that virtual image plane. And so what he does is create this virtual optical axis. We're creating a new coordinate system that intersects with the sphere at some location. Using that, attempts to adjust the apparent viewpoint of where I know the optical axis of the original camera to be, and the virtual optical axis of this new image plane that I've created, and then regress that apparent orientation. And so again, what he has now is a end-to-end training process where he can go all the way through that and produce 6 degree of freedom pose of the T handle directly in the original fisheye optical axis without having to go back through this projection. So comparing that to a baseline where you would just use a off-the-shelf sort of region of interest detector network, doing it projectively, or then doing it with the perspective approach that he's described here. So he compares all those things, and he also produces this big data set that allows him to test all of this. So in that data set, he uses these fiducials to get ground truth using a SLAM system, fit 6 degree of freedom poses to that, and then annotate everything so that he can get ultimately results on how well his deep learning 6 degree of freedom detection system works. We had multiple handles in the kind of deployment we did. So one was the Hui handles, which look like T handles. One was the Schmidt Ocean Institute handles that look more like little cylinders. But you can see here, this is just in ROS. him producing the sort of real-time production of where he believes the T-handles to be within the manipulator's frame. And then that's ground truthed with the fiducials from the April tag slam. Okay. And then he also produced some tools to visually annotate, what the detection says. So what you see there is a 3D projection of where the system believes those T-handles or grip locations to be, and are being projected obviously in real time relative to the position of the camera. Great. So if you're interested, have a look at the paper, but long story short, you can produce reasonable results that do better in terms of accuracy than the baseline approaches. And you can do this sort of directly in a much faster and less sort of complicated means, which works well because we want to deploy this in real time on ROVs, which tend to have sort of a lot of real-time constraints. Great. Okay, so here's it working in real time qualitatively. So what you see there are the detections of those T-handles and the relative positions of them projected back into the image plane. But this is all relative to the manipulator. And so this is sort of with the aim of ending up with a full end-to-end manipulation system that would let us detect and grab things in real time. So he got to deploy this, and to do that, he had to work on some pretty gnarly arms. So we used these arms that are not electric motors, and so they have all of these sort of feedback problems and jerk problems and other things. And then the other challenge is that we have stereo vehicles mounted on the vehicle and then also mounted on the wrist of the manipulators. So he was able to use this to do a stereo reconstruction of the environment and then to do a visual kinematic calibration, and then use the fisheye for object detection and visual servoing. This is the Nereid under ice vehicle that he ended up getting to deploy on. And so what you can see here are some of the challenges. The arms are actually on the doors of the vehicle. The doors kind of butterfly out. And so we had to kind of in real time try to estimate the body frame of the manipulators and then do all this work underwater. So what he's ultimately working on is a pick and place pipeline where an operator can simply click and select in sort of this virtualized environment of what we want to do, and then see what the vehicle is going to execute, and then actually confirm that it should execute it, right? These vehicles are super expensive, and so there's a lot of challenges with just letting us go open loop. And so ultimately what he landed on was proposing, this is what I'm going to do, and then have an operator do that as opposed to drive it themselves manually. So here, this is on the SOI vehicle. So we got to deploy a number of different vehicles. That's a real-time stereo point cloud. You can see some of the challenges with working underwater. There's a lot of noise in that. And then him doing various grasping manipulation maneuvers on that. And then finally here is on the Nereid vehicle. And you can see this is a slurp gun. So it's slurping up sediment samples and doing that using his system that is sort of click and collect. Finally, we iterated with Matt Walter, who does natural language work. And so he added a system that said, execute now, grab this, pull that sample, do this, and then have the vehicle go all the way through and perform that using natural language commands. Okay, that was a whirlwind tour of only a couple of projects. It went pretty fast, but I would love to take some questions if we still have some time, which looks like we do. Okay, I got to get out of this to see chat, I think. Questions, comments, concerns?
I have a question.
Please.
You mentioned, I guess earlier in your talk about your learning from simulation, the game engines, and how you would never recommend anybody do that again. But it still seems at the same time that you think there's something to learning from simulated data. So what would you argue as a replacement for just other kinds of physics-based engines or simulation engines? Or
Yeah, no, so great question. I would not recommend you use a closed source video game that is not designed for this. It's actually this really interesting challenge. So since that work came out, there have been a few Unreal Engine based simulators, notably among them Carla, which lets you do this in sort of a much more civilized way, right? So we had created modules that hacked into the actual graphics driver, and we would extract various buffers and then do things with them. It was a nightmare every time they updated the game. It broke everything. It was terrible. Carla does not have that problem. So you can just write a little Python script that pulls your images out. Great. The big challenge, and this is the thing I don't know how to get around, is when we were back in this era, we actually approached Rockstar Games, and they sent us a nice cease and desist letter and said, please stop doing this.
Yeah.
And so they were not interested in working with us to make this a product. I understand why now. I don't think I understood at the time. They sold more copies of that than any other media product has ever been sold. They made more money off that than Titanic, than anything, right? So us little rinky-dink researchers saying, "Oh, this could be another revenue stream," they were not interested. But one of the big challenges is that the photorealism of Carla and the Unreal Engine simulator that is far inferior to Grand Theft Auto 5, and that is a game that is 7 years old, 8 years old now. And so there is this real gap between the video game industry when it comes to the sophistication of the assets and the photorealism and what is available in the open source community. So no, I still think that learning from simulation is incredibly valuable and a thing that should be pursued. The only thing I think you shouldn't do is waste your time trying to hack into a closed source.
I see. Yeah.
game.
Gotcha. Yeah.
Katya, I see you have your hand up.
Yeah, so when you're taking samples, right, with a manipulator and so on, is there also an issue, or are you looking at the issue of where to take the sample, or in this particular, because obviously that's a different thing, because first of all, where to take the sample, what sample to take, and also depending, of course, if you have different consistency of the soil and so on, you may of course want to use different forces.
Yeah, it's a massive problem, and there's a couple different pieces to it. One is when you take a sample, particularly those loose sediment ones, you pick up a bunch of sediment, you obscure all the cameras, you can't see anything anymore, so you're sort of been out of luck for 5 minutes. So that's problem one, just from a practical standpoint. But then from the science standpoint, often there's sort of this interactive process that we were trying to capture. There would be a marine scientist or a exobiologist or whatever standing behind the operator. They'd say, "That looks cool, grab me a sample of that." And so it's sort of this interactive process. But then the challenge is that the ROV manipulator, had a very limited workspace. So to grab the sample where they wanted, you may need to raise up and move. And then when you do that, you pick up all the sediment, you can't see anything, you don't know where you're going to sample then. And so I think there's two parts to that. One is we ran SLAM to map the environment of the workspace. And it became really, really important because then if you did move and they said sample here, by the time the sediment settled, you can then actually really sample where they had asked for, which I think was one piece. But then secondly, thinking about this in the sort of long term, obviously for space, the communication delays mean that you're not going to have this sort of iterative loop. And so thinking about, and a lot of work has been done here and elsewhere, thinking about that sort of adaptive science, what is the right sample to take and how do I think about that, I think is a huge avenue. Certainly outside the scope of what we did, but we would love to integrate that work because I think it's an important piece to make this work, right?
Right. Because in some, we have some work with George Cantor where we're doing this adaptive sampling for plants. But of course, there is some work by Sukatman et al. And so on. And this may be an opportunity, where one says, okay, what is the best place, kind of learning the environment? Where is the best place to take the next sample? And then, of course, you navigate and then you say, okay, this is the one, and so on and so forth. So
no, exactly.
That's at a larger scale. Yeah.
Agreed.
Yeah.
So now that you're in Pittsburgh, how does your research evolve? You obviously can do rivers now. You can slither out of the water onto land and do holes in the ground, or you can aspire to go to the moon with Red. Are you going to take advantage of any of those opportunities?
I would like to try to do all of them. In fact, Winnie came to me as soon as I got here, and she had a really interesting project, which is she's looking at a cave system and wants to map a cave system. It's got sediment all in it, and it's both above water and below water. But it seems like a nice opportunity to do the same kind of 3D mapping that we try to do in these other environments, but obviously in a sort of Western PA centric way. And look, I'd love to, we'd love to try to do anything we can to kind of advance sort of the science work in outer space. So that work that I showed you there was done in the context of NASA's P-STAR and then A-STEP. I always get the order reversed. I don't know which one we got first, but those two projects. And so, the hope is that at some point the stuff we're doing here in the deep ocean will be useful in space. But it's there's a long way to go, as you can see in the sort of limited capability we have relative to terrestrial robots.
Are you going to invite us to your trips to Tahiti for field work?
You are always welcome, Chris. We're doing lots of work. It's one of the biggest impediments has been obviously the kind of lack of travel with COVID. But we used to go to some really nice locations. I would say that, the east and west coast of Australia, Thailand, cool spots, Tahiti, Bermuda. We always need somebody to carry the gear.
We could have a Robotics Institute yacht.
I don't know if Cheryl's going to let me get away with that from a spending perspective, but we'll give it a shot. Anything else, or I will let you all, I know we're running up on time here. I'll let everybody go back to enjoying Snowpocalypse 2022.
Well, if no one else is going to speak up, let's thank you for your seminar today.
Thanks a lot, Ag. Thanks, everybody. I really enjoyed it. And I look forward to seeing everybody around as we roll through the semester.
Thanks, Matt.
Bye, everybody.